Before we begin part 4, let us review the temperature time graph and the temperature concept that we discussed in part 2. We are all familiar with the graph that shows how temperature changes over time as a result of thermal energy being continuously added to a solid substance at a constant rate. At the beginning, the substance's temperature will rise until it reaches the melting point temperature, which is the temperature at which the solid starts to turn into a liquid. However, the physical process that results in the phase transition of a substance from a solid to a liquid is called melting. Once the temperature of the substance reaches its melting point, as long as heat continues to be added, the temperature will stay at the melting point until all of the solid turns into a liquid. When all solids turn into liquids, the added thermal energy raises the liquid's temperature until it reaches its boiling point, at which point the liquid begins to turn into gas via the boiling process, which occurs throughout the liquid rather than just at the surface like the evaporation process, as we discussed in part 1 of this unit. In fact, our next topic after we finish the discussion about the temperature time graph is to compare the boiling and evaporation processes based on the kinetic particle model of matter. Now, let's look at the temperature time graph as we remove thermal energy from the substance. The temperature of the substance will initially decrease until it reaches the condensation point temperature, which is the temperature at which the gas begins to turn into a liquid. However, condensation is the physical process that results in the phase transition of a substance from a gas to a liquid. Once the temperature of the substance reaches its condensation point, as long as heat continues to be removed, the temperature will stay at the condensation point until all of the gas turns into a liquid. When all gases turn into liquids, the removed thermal energy reduces the temperature of the liquid until it reaches its freezing point, at which point the liquid starts to freeze, while the temperature stays at the freezing point until all of the liquid turn into solid. After that, the more thermal energy that is removed, the lower the solid's temperature will be. Before comparing boiling with evaporation, let us first answer some questions and state some facts about evaporation.
How can we use the kinetic particle model of matter to explain evaporation?
Let's begin with a visual illustration of evaporation. In this experiment, we witness hot water in a Pyrex glass bowl. In fact, I used hot water to increase the rate of evaporation so that we could clearly see the water vapor. It is clear that the water is not at boiling temperature. However, we can see water vapor flowing out of the water's surface. Based on what we observed in that experiment, we can say that evaporation can only happen at the surface of a liquid as opposed to the boiling process, which happens throughout the liquid as we can see here. Let me now explain why evaporation happens. Because temperature is the average kinetic energy per particle, we can safely assume that some particles have more kinetic energy than others. Consequently, evaporation takes place when more energetic molecules moving close to the surface have enough energy to overcome the forces of attraction and form vapor particles in the air. Because the liquid loses its highly energized molecules to the atmosphere during the evaporation process, its average kinetic energy per molecule decreases. Therefore, the liquid's temperature decreases.
What are the factors that affect the rate of evaporation?
When comparing the rates at which the same liquid evaporates, there are a number of factors to keep in mind. The first factor is the temperature of the liquid. A higher temperature increases the rate of evaporation. In fact, when the temperature of a liquid is raised, the molecule's kinetic energy increases, and as a result, they are more likely to escape the surface of the liquid. The second factor is the surface area of the liquid. A larger surface area causes a greater rate of evaporation. Because during the evaporation, molecules can only escape the intermolecular forces of attraction at the liquid's surface. The air movement is the third factor. The rate of evaporation increases as air movement increases. Because air movement transports the newly evaporated vapor, as a result, the air dries out, and more vapor molecules can escape. The similarities and differences between the evaporation and boiling processes are summarized in that table. Please go over the table information carefully and let me know in the comments below if further clarification is required. Gas, as we now know, does not have a defined volume or shape, since its volume and shape change depending on the shape and volume of the container in which it is contained. In this illustration, some gas molecules are trapped in a cylinder by a movable piston, which allows the container volume to change by moving the piston up and down. In this illustration, I'm assuming that the gas temperature is constant. When the piston is moved up to increase the container volume, the gas molecules move further apart from each other to fill all of the available container space, as seen in the illustration. Also, as the volume increases, the pressure decreases, and as the volume decreases, the pressure increases. Actually, English scientist and chemist Robert Boyle studied this phenomenon and published his findings in 1662 with the following statement: "The volume of a fixed mass of gas is inversely proportional to its pressure, provided its temperature remains constant." Boyle's law is the name given to this statement. It is important, however, to understand why the phrase "provided its temperature remains constant" exists in Boyle's law. This is because when energy is transmitted to a gas, its temperature increases. The trapped air in the original Boyle's law experiment quickly lost energy to its surroundings and returned to room temperature. Boyle's law can be formalized mathematically as follows. The gas pressure is inversely proportional to its volume. So, the pressure of a gas equals the constant divided by the volume of the gas. That equation can be rearranged so that the product of pressure and volume is a constant. And finally, we can write Boyle's law as P1V1 equal to P2V2, which can be used in a variety of calculations. In fact, given that pressure is inversely proportional to volume, Boyle's law can be graphically expressed by plotting pressure versus 1 divided by the volume, which should result in a line that begins at the origin. But if you plot the pressure of the gas against the volume of the gas, you get a curve that looks like this. Let's put that rule into practice by working through some examples. This problem is from 2021's paper 4, Winter Exam Variant 1. Figure 3.1 shows a balloon inflated with air. The volume of the air in the balloon is 630 centimeters cube, and the pressure of the air in the balloon is 1 times 10 raised to the power of 5 pascals. The balloon is tied to a heavy stone and dropped into a lake. The balloon is pulled down quickly, and the temperature of the air inside does not change. Calculate the volume of the air when the pressure of the air is 1.4 times 10 raised to the power of 5 pascals.
Please pause the video while you attempt to solve the problem on your own, and then continue to see how the problem was solved.
When we attempt to find a solution to a problem, we begin by writing down the information that we have been given. In that problem, we get the initial conditions of pressure and volume. P1 equals 1 times 10 raised to the power of 5 pascals, and V1 equals a 630 centimeters cube, and the final condition is P2 equals 1.4 times 10 raised to the power of 5 pascals, and V2 equals as the unknown. As a quick observation with regard to that problem, we only have one unknown, which means that in order to solve it mathematically, we only need one equation. We can solve that problem by beginning with the rule that P1V1 equals P2V2, which is the only equation we need to solve the problem, because there is only one unknown in it, and then plugging in the values that we already know. And that will lead us to the solution, which is the final volume. V2 is equal to a 450 centimeter cube.
Excuse me, but how does the kinetic particle model of matter explain the fact that the pressure goes up when the volume goes down?
Alright, let me try to answer that question in a logical sequence. As long as the temperature is held constant, the average kinetic energy of gas particles remains the same. Consequently, there is no change in the net force produced when gas molecules collide with the interior of the container. We all know that surface pressure is calculated by dividing the normal net force acting on a surface by that surface's area. Therefore, the same amount of gas at the same temperature in a smaller container will result in the same normal net force acting on a smaller area, leading to a higher pressure. Let's discuss why a rise in temperature leads to a corresponding rise in pressure if we keep the volume constant. Let's first carefully monitor the results of this experiment. In this experiment, the volume of air contained in the flask is fixed. We'll start by heating the oil bath that surrounds the flask, while taking temperature and air pressure readings. As you can see, as the temperature rises, the pressure also rises. The kinetic particle model of matter could be used to explain that. As more heat energy is added to the trapped air to raise its temperature, the air molecules gain more kinetic energy, making the average kinetic energy per molecule higher. As a result, the internal surface of the flask will experience more collisions with greater force, increasing the pressure. At the beginning of the 19th century, this experiment and others like it helped establish the relationship between gas pressure and temperature. In fact, the British physicist William Thomson, who later became known as Lord Kelvin, suggested in 1848 that there must be a temperature at which the particles in gas exert no pressure on their container. He thought that when a gas reaches this temperature, its particles stop moving and stop colliding into the walls of their container. Actually, Lord Kelvin used that temperature as the basis for an absolute temperature scale. This temperature reached a low of -273 degrees Celsius, which is known as absolute zero. The Kelvin scale is widely used as a standard for temperature measurement in scientific study. The Kelvin scale actually begins at absolute zero, or 0 Kelvin, which is -273 degrees Celsius. 1 Kelvin is equal to 1 degree Celsius, and the Kelvin unit of temperature is represented by the letter K. However, unlike with degrees Celsius, there is no degree symbol. To convert the temperature from degrees Celsius to Kelvin, you need to add 273 to the temperature in degrees Celsius. Before we end our discussion about the absolute zero, I'd like to highlight some important points that aren't part of your curriculum, but are still useful to know. First and foremost, absolute temperature is primarily a theoretical concept that is derived from a combination of experimental observation and mathematical analysis. Actually, according to the principles of quantum mechanics, it is theoretically impossible for matter's atoms and molecules to cease moving at any temperature. However, absolute zero remains a fundamental concept in thermodynamics. In fact, many experimental physicists spend their careers trying to use lasers and magnetic fields to reduce temperatures to absolute zero, but they never succeed. However, in 2003, a group of scientists from the Massachusetts Institute of Technology, MIT, set a new record with a temperature of 0.45 nanokelvin. Finally, since 1954, scientists have been able to enhance their measuring techniques and determine absolute zero at -273.15 degrees Celsius. However, we will continue to use -273 as our value in our curriculum. Let's discuss how a gas's volume varies with temperature when the pressure stays constant. Let's take a look at an experiment that demonstrates this concept. In this experiment, we begin with air trapped in that long, narrow neck flask and use a short length of colored liquid to separate the gas inside the flask from the air outside, while keeping the air pressure inside the flask at atmospheric pressure. The movement of the colored liquid will indicate an increase in gas volume if we apply thermal energy to the gas inside that flask to raise its temperature, say from 10 degrees Celsius to 20 degrees Celsius. This could also be explained using the kinetic particle model, which states that an increase in thermal energy will lead to an increase in the kinetic energy of the particles, which in turn will lead to a greater degree of separation between the particles, resulting in the gas expanding. Between 1787 and 1802, a group of scientists discovered that, under constant pressure, the volume of a gas changes linearly with the change in temperature. In fact, this finding was the basis for what is now known as the Charles Law, named after Jacques Charles, a scientist who drafted the initial version of the rule that links the volume of a gas to its temperature in a work that was never published in the year 1780. But in 1802, the scientist Joseph Louis Gay published that relationship and gave Charles credit for his own research that had never been published. Actually, Charles's law appears to imply that a gas's volume will decrease to zero at a certain temperature, which can be found by measuring the gas's volume while keeping a constant pressure at various temperatures, then extrapolating the line to find the temperature. In fact, the work to determine the value of this temperature accurately started even before Charles's finding. However, it was estimated to be -273 degrees Celsius by Lord Kelvin when he invented the absolute temperature scale in 1848, as we mentioned before, when we talked about the absolute zero temperature. In mathematics, we call this relationship a linear relationship because we can represent it graphically as a straight line. However, when we plot the gas volume against the temperature in Kelvin, the relation becomes a special type of linear relation that we call directly proportional, as the line passes by the point of origin. The Charles law statement can now be written as follows: the volume occupied by a fixed amount of gas is directly proportional to its absolute temperature if the pressure remains constant.
I want you to be very careful about the temperature unit, especially when we use the Charles law in its mathematical form, because any temperature unit other than Kelvin will result in a linear relationship instead of the direct relationship that the law says should happen.
Let's express the Charles law mathematically. If the volume V is directly proportional to the temperature T in Kelvin, then the volume V is equal to a constant times the temperature T in Kelvin. As a result, we can say that the initial volume, V sub I, is equal to a constant multiplied by the initial temperature, T sub I. And the final volume, V sub F, is equal to a constant multiplied by the final temperature, T sub F. If we divided those two equations, we get V sub I over V sub F is equal to T sub I over T sub F. Or V sub I times T sub F is equal to V sub F times T sub I. Both of these equations may be used to solve problems, but please remember to use the temperature in Kelvin. Let's make sure we understand how to apply the Charles law mathematical form by working through a simple example.
A bubble of air in water has a volume of 1.32 centimeters cube when the water temperature is 25 degrees Celsius. If the air bubble is still at the same depth after its volume has expanded to 1.38 centimeters cube, calculate its temperature in degrees Celsius. As usual, we will start by writing down the given information. The initial volume V sub I is equal to 1.32 centimeters cube. The final volume V sub F is equal to 1.38 centimeters cube. The initial temperature T sub I is equal to 25 degrees Celsius plus 273 to convert it to kelvins, so we can apply Charles's law, which is equal to 298 kelvins. And finally, we don't know the final temperature. The equation of the Charles law, V sub I over V sub F, is equal to T sub I over T sub F. Plug in the numbers, and we get T sub F equals 311.5 kelvins. Subtract 273 and we get 38.5 degrees Celsius. In the next part of the thermal energy unit, we will learn about the transfer of thermal energy and the greenhouse effect. See you soon.
Goodbye.